to clouds. Badhiya. Then I have to share the screen. Yeah, that's the screen I have to share. Do you have book with you?
Take about 5 minutes to just bring my book, but you can start. I'll take it.
No, you take
Just
a book so that we can simultaneously referring to the same page.
sir, this is book two. Energy performance.
No, this is book 4.
Book. Oh, sorry. Give me a minute.
Book 4, chapter 3. If you go as per
Got it, sir.
page book, the page book is 43. And if it is a soft copy, then it is 67.
नहीं सर हार्ड कॉपी मिला है मेरे पास.
Okay.
I'm in that same page. Yes.
Yes, 43. Okay. The purpose of this particular chapter is a revision what we learn in book 2. Book 2, the same chapter we have studied cogeneration and steam turbines as well as gas turbines, the topping cycle, bottoming cycle, the combined cycle plants, no, the combined heat and power plants. And then the secondary side of these either using steam turbine or the gas turbine. And then we have also clarified the concepts regarding topping cycle, where we have said when the first electricity is produced, it's the topping cycle. When first heat is produced and subsequently on waste heat when we produce electricity, it is bottoming cycle. Okay, so all these things are already known. So in this chapter, I will give stress more on what we don't know. Right, the purpose of performance test is already known. We have taken performance tests of boiler, turbine, individual equipments, no, EHV equipments and heat exchangers. Sorry. So this is just a revision. So let us look at the formulae which are used in book 2. Oh, sorry. Yes. Let us understand the phrases because you will have to calculate based on these formula. The small 5-mark numericals if are there, they may give you a 10-mark question with 2 numericals, 5 marks each, A and B. So what is overall plant performance? The overall plant performance is measured in 2 parameters. One is overall plant fuel rate. Fuel rate name itself suggests the unit is kg per kWh or sm cube per kWh. When you are using a solid fuel, for example, coal, biomass, rice husk, or other, which is measured in kgs. So if you are operating a plant, boiler or the subsequent entire plant, you are using heat generated by the fuel. So fuel in kgs multiplied by the gross calorific value of that fuel will give you the total heat you are putting into the system. So if a system is operating, maybe they are producing electricity, they may be producing only the steam. When they say what is fuel rate, it means per generated kWh requires how much fuel for that particular process. So it's a kg per kWh. When you are using gas, instead of kg, it is the standard cubic meter. How many cubic meters of gas you require to generate 1 kWh. What the ratio will be? Denominator, of course, is power output in kW. Numerator is fuel consumption in kgs. per hour or SMQs per hour. Suppose 100 kgs are required to generate, for example, 10 kW power. So 100 by 10, so per kW is generated. Here H is not considered. No? You will ask me the question. In denominator, it is kW and not H. Because the upper and lower, both the parameters, denominator, numerator, are for per hour basis. Therefore, kW is also per hour basis. So separately, H is not written there. Multiplied by H you will get the energy unit. So that is overall fuel rate. Then what is the energy utilization factor? What is the energy utilization factor? The total input heat and what is the useful output. Useful output is in numerator. In denominator, it is the heat input. Like any efficiency use. So total heat input will be how much? Fuel multiplied by kgs per hour, that is fuel, into the gross calorific value of the fuel. That will be denominator. And in the upper, electrical output as well as the heat output or steam output. So the electrical output is kWh, which is equivalent to 860 kilocalories. So whatever is the energy generated, you multiply it by 860. Why? Because the numerator and denominator has to be in the same units. If the denominator is in kilocalories, how do you get that? Fuel in kgs multiplied by the gross calorific value. That is the denominator. In upper also, when you see the utilization of that heat in generating electricity, that is so much kWh into 860 is the conversion factor to heat. Plus thermal output, normally it is in the form of steam. So how do you do that? So much kgs of or tons of steam generated multiplied by the heat content in that steam. That is the total heat per kg multiplied by kgs of steam, like that. You will get again the kilocalories. You take a ratio that will give you some percentage, say 50%, 40%, 60%, whatever. That will depend on how much useful heat you have generated out of the total heat input in the process. Right. Next, the turbine stage isentropic efficiency. The concept of isentropic I have explained. But to remind, isentropic is the ideal conditions in which the steam is allowed to expand. In reality, the actual expansion curve and the isentropic curve, they differ. And how it is measured? When you calculate the efficiency means what is the actual drop you achieved upon what the ideal drop you should have achieved, right? And ideal means isentropic. So numerator is actual enthalpy drop across turbine upon the isentropic drop across the turbine. Take a ratio, it will give you isentropic efficiency. Overall plant heat rate. When you say overall, that means you are taking input and output condition of the entire process, not only for boiler, not only for turbine, not only for heat exchanger. Yes, total heat input and the total useful heat output. Got it? So that is the boundary of the process in and out. Now we have learned if you want to calculate total heat rate without considering any inefficiencies inside or whatever may be, lump sum, how will you get the heat input? Fuel input into the gross calorific value. Fuel input, how will you get? That's we have already calculated the plant fuel rate. That means the plant requires so much fuels, so much kgs per kWh into calorific value of the heat. That is the overall heat rate. That means we have calculated overall plant fuel rate, and if you want to convert it into heat rate, you multiply by GCV. Remember, all these calculations we do with GCV and not LCV. LCV is the lower calorific value, which we do not take into consideration here. Then, in case of solid fuel, if it is gas turbine, heat recovery steam generator, that means it is a double cycle, right? Binary cycle. First cycle, the fuel going into the gas turbine, gas is burned, hot gases are going to the heat recovery steam generator, and steam is generated. So how will you calculate the overall? Overall plant heat rate is the overall plant fuel rate. That means so many cubic meters of gas supplied to the turbine multiplied by the NCV of gas. Remember, the gaseous fuels calculations involve NCV of gas, net calorific value. That is normally given for calculations. In input data, you will find that the parameters are given. And the boiler efficiency, which is not using any fuel, but it is using the hot gases they are coming out of the gas turbine. How will you calculate the efficiency? Steam flow rate. Always remember, whenever you think of efficiency, the numerator is useful output upon the total input, right? Out of total input, what is the useful output? That ratio gives you efficiency always. So what is useful output by a boiler? It is the steam flow rate, so many kgs per hour. And what is the heat content per kg? Enthalpy of steam minus enthalpy of feed water. Because if feed water is preheated, that heat is not given by the fuel. Fuel is giving the difference between that. Therefore, the total heat of steam minus the heat of feed water, which is normally the temperature it shows, because the specific heat of water is 1, upon the exhaust gas which is coming out of the turbine multiplied by the lower enthalpy into auxiliary fuel into GCV. If you are using auxiliary fuel to boost up the steam generation, you will have to take into consideration the fuel value input by that fuel, heat value. If there is no auxiliary fuel supplied, then this bracket is 0. You have to only take into consideration exhaust gas flow rate, so many cubic meters per hour, into the gas enthalpy, right? Now, these standards, okay, you can forget SSME standards. Field testing procedure, how it is done, you read through it. How do you do it? Normally, thumb rule is whenever you want to test any equipment for performance test, it should be conducted at a steady state level. Normally 8 hours test, some people insist on 24-hour test. We used to insist on 72 hours test because it was a very large thermal power plant. So we will take number of readings, hourly, half hourly, 15 minutes reading, arrive at an average reading, find out what is the average level of performance. So test duration is a optional thing. The auditor can always decide at what duration it should take. Then measurements and data collection. These are the instruments used for measuring different type of parameters. For example, steam flow meter normally used for orifice flow meters. There are different, but steam flow meters, the standardized method of measurement is using this instrument. Then fuel flow, volumetric measurements or mass flow measurements per kilo kgs per hour flow. That means you need weighing meters on which either they are on running belt or they are volumetric. Air flows are measured by Venturi's. The flue gas analysis is done by zirconium probe oxygen analyzer. This you will have to remember. These are logically you can answer the first three. The fourth you will have to remember because you have not used it, but you have to remember zirconium. Then unburnt analysis. That means some carbon particles which are not burned in the furnace fall down in the ash. And therefore, ash you have to analyze to find out how much percentage of unburned particle is there. That is done by gravimetric analysis. And all temperatures are measured with thermocouple. The mercury in glass thermometers are useless for high temperatures because here we are dealing with temperatures always more than 100 degrees. So thermocouple is the standard method of temperature measurement. Sometimes in multiple choice question, they may refer to these, what instrument you will use for what. Then cooling water flow, the orifice flow meters or the channel flows or the weirs, no? Then pressure, Borden pressure gauge. These are the standard pressure gauges nowadays. Some electronic gauges are also coming, but since this book edition is in 2015, the latest equipments are not added here. But anyway, since it is in the book, you write the answer. Hello, hello, Gaude, please unmute yourself. Then comes the, what is it? You have a problem? Hello.
Sir, I guess he's on call or something, unmuted accidentally.
Oh, but he should unmute, I mean, mute himself because he has not muted himself, so that is why it's disturbing. Anyway, condensate like any water flow, it's a orifice flow meter. Then comes the thermal energy. What are the flow, pressure, and temperature? What parameters you should carefully look at when you are auditing something? When you audit, when you measure steam, you will have to measure the flow of steam, pressure of steam, and temperature. Why these three? Hello, Mr. Manish, can you hear me? Anyway, so these three parameters gives you the total heat content in the steam. Therefore, these three readings to be taken accurately. Then fuel input to boiler or gas turbine, it is only the flow, kg per hour or the cubic meters per hour. Combustion air is again flow, pressure, temperature. Why? Because we want to know what is the heat given by the combustion air to the furnace. Then extraction steam in the process. Wherever steam is involved, take three readings: flow, pressure, temperature. Flow, pressure, temperature. Condensate from the steam is always two parameters. There is no need to measure the pressure because the uh, condensate coming from turbine has no pressure, it is in vacuum pressure. Turbine bypass steam, again, how much kgs it has bypassed, that you have to measure. Flue gas to HRSG, only two. What are they? They are pressure and temperature. Exit flue gas, for composition purposes, you have to know the temperature. Then cooling water to condenser, all these three, because we have to calculate what is the heat rejected. So logically, whenever look at the parameters to be monitored, you can find out what parameters are to be monitored depending on the item you are measuring in a energy audit test. The electrical energy, how do you measure? Total power generation from trial period, that is the test period, hourly average power generation, quantity of power input from utility, auxiliary is power consumption. So you are taking a mass and energy balance. What you are doing in performance test, doing a mass and energy balance for all parameters. Now, calculation for steam turbine cogeneration system. This is a approximate block diagram. What happens in a steam turbine cogeneration? Boiler is fed either with a fuel, biomass fuel or the waste product. Steam is generated, supplied to the turbine. The same shaft generator is connected. So turbine and generator, they are on the same axis. Now, when you are doing the turbine used for cogeneration, that means what? You are generating power as well as you are generating heat in the form of steam that is given to the process. So what are the main points? First, you should know how much is the total Q, that is total steam weight in kgs per hour. H1 is the total heat content in that steam. So when you multiply Q1 into H1, you get the total kilocalories input to the turbine. Got it? Now, this H1 Q1 steam is allowed to expand to a condensate level, exhaust level. But in between, you want to use part of the steam for process. So you take a extraction. This extraction has a temperature of H2. This is H1 live steam. This is H2 extraction steam. And this is the third temperature, which is the temperature of exhaust steam. Right. Now this Q is divided partly in Q2 and partly in Q3. So Q1 is equal to Q2 plus Q3. Now, when you know quantity and the total heat anywhere, you can always multiply and calculate what is the heat equivalent. So total heat was Q1 into H1, out of which Q2 into H2 is given to the extraction and Q3 into H3 is given to the condenser. Always keep your concepts clear and understand. Now, this balance heat Q1 H1 minus H2 minus H3, this heat and this heat, still there is a difference between this and these two. That difference has gone to generating electricity. So here suppose the kWh generated multiplied by 860, so much kilocalories have gone in producing electricity. So total kilocalories here is divided into 1, 2, 3 parts. One goes for electrical generation, one goes for extraction steam for the process, and third goes to the condenser. This condenser heat is rejected to a cooling water. The cooling tower is here and hot water is going to the cooling tower, coming down, getting cooled. The cool water goes here and the circuit goes on, thereby taking out the latent heat into the condenser steam and exposing it to the atmosphere. This is what the process flow diagram of a cogeneration plant, where it is a topping cycle. That means what? First electricity is generated and the tapping from heat then goes to the process. So this is a topping cycle for a cogeneration plant. Here is the concept clear for enthalpy. This is isentropic expansion from H1 to H2 isentropic. How does it affect? You take a vertical, I mean horizontal right angle diagonal here on the scale. So ideally, this H1 should have dropped when it is dropping from pressure 1 to pressure 2. The heat drop should be like this straight, isentropic, ideally. Why ideally? Because then there is no losses, no friction loss, and so many losses occurring in turbine. They are ignored, and straight away it should have gone here. Now, what is the difference between this curve? This is the actual curve. This is how actually it has dropped. You take a tangent from this point, it will be somewhere here, whereas ideally it should have been here. This difference between the two is the inefficiency or the loss in expansion levels. So you got it. Ideally, when you want to find out the efficiency of this turbine stage, it should have dropped the heat like this, which is a larger quantity. But actually it has dropped to this. The difference between two is the inefficiency. That means on the numerator, this is actually obtained. On the denominator, the isentropic drop will give you the efficiency of the turbine stage. Right. Now, calculate the heat extraction in turbine at each stage. How many stages are there? H1, H2, H3. Steam enthalpy at turbine inlet, H1. This H1 is the total heat contained in the steam per kg of live steam that is coming into the, after coming out of boiler and entering into turbine. First extraction, that means some pressure and temperature given to the process heat. And lastly, the condensing. This is H3. This is the same question I have explained here. So H1, H2, H3 conceptually we understand. Then heat extraction from inlet to extraction. What is the heat extracted? H1, H2, Q1, Q2. So Q1 into H1 minus these two. What is the heat actually gone only this pipe? It is the Q2 into H2. So much has been drained. So when you think of leaving it to the system, extraction, how much extraction is taking the heat? So much kilocalories per kg. What is the heat going to the condenser? H2 minus H3. That is it. Then comes the step 2 from the Mollier diagram. Now, Mollier diagram we are not allowed to refer in the paper. So the extraction, rather the parameter is already given to you ready-made. Plot the turbine inlet condition, outlet condition. We are not going to do any of this. The values are already given. So turbine efficiency, heat extraction actual, heat extraction theoretical. Theoretical is isentropic, right? So here it is H2 isentropic. Whereas actual H1, H2. What is H1, H2? Go back to it. See, this H1 inlet, H2 outlet multiplied by Q2. But this H2 is actual, whereas it should have been H2 isentropic. Got it? H2 isentropic is always greater than H2 actual. Therefore, when you calculate efficiency, actual upon isentropic. This is actual upon isentropic. What is isentropic? H1 minus H2 isentropic, and on the upper side H1 minus H2 actual. That gives you a efficiency of extraction. Then efficiency of condensate is heat extraction actual upon heat extraction theoretical. Same thing, same formula. You use it if there are double extraction turbine, triple extraction turbines sometimes, sometimes a back pressure turbine. The formula is same. What is actual and what is isentropic? You take a ratio, you get the efficiency. Then to calculate the turbine power output. Now we have seen what is the output. Output is given by the electrical generator. That is number of kWh generated. So how they have calculated? To calculate the where is that? efficiency is to calculate turbine power output P. P turbine. P turbine is equal to Q1 live steam flow multiplied by H1 minus H2 Q3 H2 minus H3 upon 860, which is the kilocalorie equivalent. Now, why this 1000? Because the steam parameters many times are given in tons and you have to convert them into kgs. Remember, when calculations are done in total, you must keep the units upper and lower, denominator and numerator same, right? So Q1, Q2, Q3 is kg per hour, enthalpy kilocalories per kg, and this is the 860 into 1000. Step 5 is to calculate the generator power output. Generator power output is the turbine multiplied by the number of efficiencies. The generator power output is equal to in megawatts, right? It is, remember, megawatts. And when you apply it 860, it will be kilowatts. Okay, it's not here, but see, power output multiplied by this power output is PT, that is power output of turbine, which we have calculated here. It's a turbine. So we want to find out what is the actual generator output. So turbine output into efficiency of mechanical efficiency of turbine, efficiency of gearbox, efficiency of generator, then only you can arrive at a correct generator output. See, mechanical efficiency of turbine efficiency M, efficiency gearbox, efficiency generator itself. Threes. So if you are given only one parameter and three efficiencies, you can calculate how much is the power output at the generator terminal. Now, same example, which I have explained conceptually, is given here. Example 3.6.1. From the data given for an extraction condensing turbine, right? One extraction and condensing. Calculate stage-wise isentropic efficiency and power output. See, the parameters are given. Mainstream parameters, pressure, temperature. This is pressure, this is temperature, this is flow. It is in tons per hour. When you calculate, you will have to convert it into kgs per hour because the all other parameters are in kg, kilocalories per kg. This is the heat unit. So if you want to convert this flow into how much kilocalories per hour, so tons per hour multiplied by 1000, that is 19200 kgs multiplied by 807.9, that's the total heat in that steam, will give you input in the main steam. First extraction, again same thing, it is tons per hour, you convert it. Condenser, same. See, this left hand side, same, right? Condenser vacuum, he says, because the kg per centimeter square gauge goes negative. Temperature 45, tons per hour flow, so much. Dryness fraction. Why dryness fraction? If you want to calculate it, the total heat content. But it is not necessary, this whole thing, because he has already given you the total heat 561 and isentropic it is 534. This is the drop, this is actual drop. So the calculations, as we have seen the formulae, what is the extraction stage efficiency? Same formula, actual enthalpy drop upon isentropic drop. The parameters fill in, you can correlate with what is in the data and then you will realize all these equations. I will not go into it because this is the exercise. You yourself have to do it at home, otherwise you will not remember. I may explain here and then you will be losing the importance of it. When you do yourself, then only you will understand. Okay. Then this is second example. It's a very simple. Overall plant fuel rate. What is the overall plant fuel rate? output upon input. How much fuel is given for how much input. If the output is kWh and fuel input is coal, what is the fuel rate? How many kgs of coal or tons of coal is used in this plant for a fixed output? So many tons per hour, that's the fuel rate. So many kgs per hour, say fuel rate. So many cubic meters of gas per hour, that is the fuel rate. And when you want to calculate the heat rate, fuel rate into the gross calorific value. That will give you heat rate. That means instead of saying so many kgs per hour or tons per hour coal, that is the fuel rate, you can say how much is the heat input, what is the rate of kilocalories per hour. That you can find out when you convert fuel multiplied by gross calorific value, that will give you total kilocalorie. Right, test duration is 4. You read through this gas turbine compressor inlet conditions. The fuel data again here given. The all standardized data, everything is given here. What you have to do it, correctly fit the parameter into the correct formula. And while doing so, check the units. If it is metric tons per hour, convert it into kgs per hour. Right? Pressure is in so much, temperature is so much, flow is so much. So either you can calculate total heat content with the steam tables which are not with you. So they will give you the total heat content at this parameter. WHRB exit or the, what is WHRB? Waste heat recovery boiler. Remember the short forms because in paper they don't give long form. They will give you only this part and you may be confused what is this instrument, right? So feed water inlet parameters. The flow here is already given in kgs. You could have given it in 9.605 tons, but he has said in kgs already. So always remember, pay attention to the units they are given and then correctly use it. Now to calculate overall plant heat rate, fuel rate, so much gas is used per hour. That is the fuel consumption, that is the fuel rate. How the heat has come as we calculate the upwards fuel rate. It may be downwards. Determine, oh, it is determination of overall plant fuel rate, electrical power output, overall plant fuel rate is given. Now let us see heat rate. Overall plant heat rate kilocalories per kWh is equal to so much is the fuel rate multiplied by the calorific value. That will give you so much kilocalories per kWh depending on what type of fuel you are using. Thermal efficiency calculations of HRSG. Now, I have given you the explanation for WHRB, Waste Heat Recovery Boiler, right? Waste Heat Recovery Boiler. This name is used when in a topping cycle, the exhaust, right? The steam, not steam, the furnace waste gas is going to the waste heat recovery boiler. Whereas here, the name is slightly different. Heat recovery steam generator. Instead of boiler, they have said steam generator, HG. There it is WRSB. Meaning is same. Only thing, the difference is in the nomenclatures. So efficiency of a steam boiler is the steam flow rate multiplied by full, I mean the fresh steam enthalpy minus feed water enthalpy upon how the total heat is calculated, exhaust gas flow rate multiplied by the enthalpy, that is total heat, plus auxiliary fuel if used. Now, in this example, he says there is no auxiliary fuel used somewhere in the data. Where is the input? I just read it. Anyway, you go through it, and therefore the lower one bracket, this auxiliary fuel is not used, so this is 0. What you have to calculate is exhaust steam flow rate into the enthalpy. Now this is the steam, chimney not gas flow rate. 0.25 is the specific heat, and 542 is the latent heat into the steam. Okay, then only the flow rates you can compare with that. This is the efficiency. This is the total heat upon useful heat output. Okay, that is therefore giving you a 75% ratio. You check all these parameters which are already given. One word of caution is this 0.25 is not given in your input data, but you have to remember it is the specific heat. What is specific heat for water? It is 1. What is the specific heat for gas? It is 0.25. Remember all this. So also this 542 you will not find anywhere in the calculations. 540 is the latent heat content at atmospheric pressure per kg of steam. As you increase the pressure, the latent heat comes down or goes up depending on whether you are reducing the pressure, we are increasing the pressure. So in efficiency of HRSG, this has come. Yeah, here is the sentence. No auxiliary fuel used in this case. So auxiliary fuel calculation is 0. Whenever you solve a problem and you do not take any value for this particular bracket, you mention in writing that no auxiliary fuel is used. Hence, this calculation is 0. Okay. Then energy utilization factor. What is that? P energy, power electrical plus heat, Q quantity of heat upon Q1. The fresh steam given is divided into two purposes. One purpose is electrical energy, which is equivalent to 860 equivalent, plus the steam. Steam is already in the terms of kilocalories per kg. So you convert this power electrical into kilocalories per kg and divide it by the QF. What is that? QF is the total heat input to the boiler, HRSG boiler or the turbine. This is the quantity of steam. This is the calorific value of steam, total heat content. I will not say calorific value. The heat content per kg of steam. And what is the useful? This is the generation 3994.5 kWh into 860. Many times they will give you 3.994 megawatts. So you have to multiply by 1000 to get them kilowatts hour. Then 860 plus 9145 into this difference, thermal. That is the temperature of the steam minus the enthalpy of the water, feed water going into it. All these values are given here. You just place them in a correct way. So this is one example. If you solve this example, which is already given here, solved, and understand each stage by putting the correct parameters, then your concept will be further cleared. In exam, same example will come, but the parameters numbers will be different. Instead of 105, it may be 120, 678, it may be 700, something like that. But the formula used are same. Again, a tip. This is book 4 and paper 4. It's a open book examination. All these pages and the book along with formula is available for you to referring. You can always, when you come across, you read the problem in the question paper, you immediately know, oh, this is the formula to be used. You know where the formula is. Immediately start putting the input values in correct formula and you are done with it. The only hitch is the paper has only 2 hours time given to you for 100 marks. Now, many students or participants who are studying, they never refer the book frequently. You should refer it so frequently that you immediately know the page on which this formula is there. If you do not refer frequently, you will lose a lot of important time in searching the formula, right? And then you may not be able to complete your complete question paper. The time will be short and then you may not be getting the adequate marks. So keep it a practice. Find out which formula is where it is and then understand the correct value given into the input data. Input data, third check is to check the correctness of the units. Deliberately, they will give you quantities in different units and therefore you will have to suitably correct those units before they are being used there. Right. Now, case study of bottoming cycle. So far, we have seen the topping cycle. That means the electricity was generated first and then waste heat was used for the process. Here, it is the process is used first and waste heat is going for power generation. This is a bottoming cycle. Now, where this bottoming cycle is applicable, particularly in glass industry, particularly in cement industry, that means what is the thumb rule? Thumb rule is where the process heat required is very, very high temperature. Cement industry is using the heat for roasting their gypsum and therefore there the temperature they require is much more, 1000 degrees. And therefore, when the fuel is burned, the highest temperature zone is used for the process, roasting process or the furnaces, right? And when it is exhausted, the exhaust gas temperature is very high, 700, 750 degrees centigrade. This gas with so much temperature cannot be wasted into the atmosphere. So they divert this gas to HRSG, that means heat recovery steam generators, HRSG, or waste heat recovery boilers, WHRB. And those boilers will generate steam from the water using the heat in waste gases. So electricity generation is subsequent. First use is for the process, bottoming cycle. Now, waste heat sources in a cement plant, you read this. This is the explanation in the kiln, what they are doing, what they are using. This is a block diagram, which is very simple to understand. Here, the kiln is a furnace where the fuel is burned, very high temperature gases are exhausted. Those gases are used for generating steam in pH boilers or AQC boilers. And both boilers steam generated is connected together. High pressure steam goes to the turbine. Now, once the steam is generated, the further cycle is same like any steam turbine. The steam is allowed to enter into inlet of turbine. It is expanded, exhausted into condenser. The condenser converts the steam into water. The water is going through the feed pump and the water is supplied to both the boilers, this boiler and this boiler. It's as simple as that block diagram. So the process, whether it is a gas turbine outlet, whether it is a kiln outlet, whether it is a glass furnace outlet, the heat is allowed to pass through the turbines, boilers, where no fuel is used. The heat in the waste gases is used for converting water into steam. Here, this steam goes to the turbine, and once the turbine gets a steam, all our calculations of a topping cycle or bottoming cycle are same. They may even use this steam for process steam if there is a composite industry. In this diagram, he has not taken any extraction, but it is possible. You can take extraction here and use it. Here it is a condensing turbine. The turbine is generating power at the generator end. The exhaust steam cool down because of the cooling water going to say cooling tower, and this water is going back. This is in short. What you have to remember is these are all heat recovery methods to improve the overall efficiency. How gainfully you can utilize the entire heat supplied by the fuel, right? Then what are the calculation formulas? Calculation of power generation potential. That means how much heat can be supplied to the turbine and how much generator we can produce in kWh. Now you already know how to calculate that. If you know the heat, that part of the heat which is going to the generator, you can divide those kilocalories by 860, you will get kWh. So much is the power generation. But how do you know how much heat is going to the generator? What you have to do? Heat input here and heat exhausted into the condenser. Take a difference, it goes to the generator. If efficiencies are given, then mechanical efficiency of the turbine and then gearbox and then generator multiplied by efficiencies and you will get the net generator output. So what is the potential here? If you have given these other details, you can calculate the heat. Once you calculate the heat, you can calculate how much power can be generated. So what details he has given? Kiln capacity, that means this capacity, 4,300 tons per day. He has immediately converted into so many tons per hour. While calculating, you will have to even convert these tons into kgs per hour. Number of stages and all that preheating you leave aside. Preheater exit gas details. This preheater is going to PH boiler, preheater gas, right? Preheater gas, that is the high temperature gas going to the APH boiler. So volume is so many cubic meters per hour, specific heat, so many kilocalories per kg per degree centigrade. Remember, here it is kilocalories per kg, whereas all the parameters given here are tons per hour. Okay. Now inlet temperature is so much. Outlet temperature of WRH is 195. So this is the heat recovery. Cooler exit gas. So much volume, so much heat capacity, temperatures, and the outlet temperature. All these parameters are given. If you conceptually understand what is to be done, then you will find all parameters are given. You have to put them in the formula and calculate. Here, they have given the conversion efficiencies of preheater section 20%, cooler section 21%. Then how will you calculate? Heat recoverable in preheater gas, mass of preheater gas, calorie C is the temperature of gas, and delta T is the temperature difference. That is C is specific heat, 0.316, right? Then so much million kilocalories per hour is the heat recoverable. Total power generation considering 20% efficiency in preheater circuit. So much million kilocalories divided by 860 kilocalories with the 20% efficiency. This is 860 kilocalories. The total power generation possible is so many million kilocalories. Million is 10 raised to 6 divided by 860, that is 1.383. So much megawatts can be generated by recoverable heat from preheater gas. Then next gas, cooler gas. mCp delta T. M is the mass, so many kgs per hour. Cp is the specific heat of the gas, and then delta T is the temperature difference. You got so many million kilocalories, but the use, that is the conversion efficiency, is only 21%. So take out only 21% of this value is so much. Now this value converted into electricity means so much kilocalories. This is million kilocalories converted into kilocalories by multiplying 10 raised to 6 upon 860. So 1.615. So by one generator, see, it is, that means the heat necessary for generating the power, so much given from this, so much given from this. Together, the steam is given to turbine. So what is the total heat input, right? So the total heat input, cooler gas, you can get the conversions, preheater gas and cooler gas details. These are here. We have already calculated. So taken together, we have a capacity, possible capacity to generate 3 megawatts. This earlier, this one 1.383, and by this it is 1.615. Taken together 3 megawatts you can generate. That is the potential to generate electricity. That is the first answer. Right? What is that? Calculate, calculation for power generation potential. How much power can be generated? You can calculate. Then solve example on the same topping cycle as well as bottoming cycle. These are two examples he has solved, and these are the examples. Again, I will repeat my instructions. You understand this example which is solved and given in the book. Try to solve it yourself. Again, go back to the book where you have not understood. Find out he has solved it till you get a correct answer to the, like the book, you should be able to solve on your own without referring to the book. With that, you will get the confidence to solve any problem which will be coming only with the different figures. The formula is same. You will also know where the formula is. You can correctly, without losing much time, will be able to refer the book and solve it. So with this is just a revision which I have done. In book 2, we have already seen the cogeneration steam turbines and cogeneration gas turbines. Cogeneration also from the bagasse, from different fuels, there are different rates of fuel, that is the kilocalorie values, gross calorific values. So with this, I will briefly try to give you answers for this question. That is also actually I don't like, because that's like a spoon feeding. Unless you do it yourself, there is a lack of confidence always. I always say that people get confused because they have not practiced it. Now, reading these questions, say short answer questions, 10 questions are given here. What is meant by overall plant heat rate and what is its significance?
Sir, so this particular chapter, we won't get any multiple choice. Is that so?
It may not, because question paper 4 will give you some 10 marks multiple choice, as I
Oh,
heard.
yeah.
You will
Correct.
have to check in the past examination papers.
Hmm.
The links are already given to you. So
Yes.
if there are 10 multiple choice question, one they may ask on this issue. One may be on other performance assessment. So what is mean by overall plant heat rate and what is its significance? Just now I have told you what is overall plant heat rate. How much heat per hour is put into the plant? Overall. That means what? How much fuel is input per hour multiplied by the gross calorific value of that fuel will give you overall plant heat rate. Got it?
Yes, sir.
Overall plant fuel rate multiplied by the gross calorific value fuel will give you heat rate. What is its significance? It allows you the
Capacity,
calculations. Huh?
efficiency of the plant.
Yeah. In the performance efficiency, it is most important. How much per hour you are putting it and what is your output. Draw the schematic diagram of topping cycle. What is topping cycle? First you generate power and then the other is the process it. That is the topping cycle. That means when you draw this cycle, it is already drawn here. If you go back to the topping cycle. Yeah, this is topping cycle. Because here the steam is going for generating power first and then extraction steam going to the process, right? So the priority here is the power output first and then secondary. Whereas bottoming cycle, this you have seen here. Here. First, the kiln is used. That means the process is using the heat and the waste gases going through these boilers are generating steam, secondary. And then this is for generator.
This is more like a working of a heart.
That you can decide what convenient to
At least I
remember.
can
No?
remember, sir, in that case.
Yeah. Ultimately, you have to remember. That is what is. All our exam system is the memory test, nothing else. Okay. Between back pressure turbine and condensing turbine, which will have more power generation efficiency? What is
Back.
the difference between back pressure turbine and condensing turbine? That should be clear in your mind. Back pressure turbine means the turbine is not exhausting into condenser. It is exhausting at a pressure. So the heat is entirely used for process. Part of it may go to the generator, but the bulk of it. Why I am saying bulk? Because in condensing turbine, the steam condensing into condenser is losing all its latent heat to the cooling water.
Mm.
Why the efficiency of a thermal plant is as low as 30% or 33%? Because latent heat is the largest single component of heat. 540 kilocalories per kg of steam goes to the waste. And whatever is in the pressure steam, that only is used by the generator. Therefore, when you want to generate only electrical power generator, then condensing turbine will be doing more power generation because it is trying to extract the heat in steam by the lowest possible pressure drop. It enters at say 150 kg and goes to condenser at negative pressure. So the largest portion of the steam is used for generating the power. So it is profitable to use a condensing turbine for electrical generation. Conversely, if they ask you what is the type of turbine you will use for mechanical power, mechanical power, that means the heat utilization of that system, you will always get a back pressure turbine uses the heat more. Condensing turbine uses electrical generation more. So depending on what is the question. The question here is power generation efficiency. And when they have asked me the reason, I will say the pressure steam is allowed to expand from highest pressure to negative pressure. It's a long range through which it is expanded and therefore the mechanical work done by the turbine is more in case of a condensing turbine, whereas back pressure turbine gives more work in heat to the process. 4. What is meant by turbine stage isentropic efficiency? Go to the diagram, draw it, try to draw it. Always carry a pencil and a scale with, of course, eraser to when you go for this paper. You may have to draw many diagrams, like say, write a block diagram as he has said. So you should be able to. Similarly, some graphs for representative purposes. It may not be to the scale. Which parameter is assumed to remain constant in ideal expansion through steam turbine?
Sir, sorry to interrupt. So for the question four, it's mostly this flow kind of a thing, right? In entropy and enthalpy.
Meant by what I didn't get
No,
your question.
for example, okay. If there is any graphical representation of this
Huh? Huh?
particular answer we are talking about, so
Hmm.
it can be very much similar to this Molar's diagram, right? Like enthalpy, entropy.
Yes. Same, no, the red diagram which is here. Same diagram you have to draw. Because that diagram gives you what parameters remain constant. See,
Uh,
this is entropy. This remains constant. है ना? The
sir.
value of entropy at this pressure and this pressure also remains constant in the expansion. Whereas pressures are varying, heat content is varying, but entropy is constant. So Molar diagram gives you the answer to question 4. What remains constant is the entropy. Because this type of vertical expansion assumes there are no efficiencies, no frictional losses, nothing. This is a ideal expansion of a steam
Mm.
from pressure 1 to pressure 2. You have to draw this diagram and show a perpendicular line which is vertical to the entropy scale, right? Entropy axis.
Perpendicular to entropy and parallel to enthalpy.
Yes. This is the question 4 answer. Right. Question 5. Which parameter is assumed to remain constant? Yeah, we have seen. The same. What remains constant is the entropy. Then starting from steam input to turbine, what are the various efficiencies considered in determining the electrical power? What is that? Mechanical efficiency of turbine, then the gearbox efficiency, and then the efficiency of the generator itself. Now, these are, he has already given the list of efficiencies you have to multiply. Where is that? Referring to the soft copies is always troublesome. You can always quickly refer to hard copies. Where is that efficiency calculation? We have seen it. You can refer to your book also so that you can find it quicker than me. And make it a practice. Always refer to the book, frequently going through these. Oh, here it is. See, generator power output. How many efficiencies you have to consider? Mechanical efficiency of the turbine, mechanical efficiency of the gearbox, mechanical efficiency of the generator.
Generator.
Three efficiencies. When their values are given, you can put into the formula and take it out. Right. Then, which was the question? Yeah.
Six we disturb, sir. Like seven we have to do it.
Yes. Now, 7, between a thermal power plant and a cogeneration plant with a back pressure turbine, which will give you a higher heat rate. Which will you? Come on, guess it.
Between thermal power plant and cogeneration.
Cogeneration, of course, will give. And then why? Because we are using the heat
Waste energy to process a different.
process limit.
Mm.
Yes. Then an industry with cogeneration system requires process steam at 12 bar. Bar means kg per centimeter square and 3 bar, 2 extractions. What type of turbine is most suitable for this application?
An industry process to move
It
to
will be a back pressure turbine with one extraction at the 12 bar and exhaust at 3
three
bar.
bar.
Right? That's the answer. The cogeneration plant with a back pressure turbine has a constant steam demand and fluctuating power demand. What options are available to meet the fluctuating power demand? We have seen here in cogeneration. I have said if the power is fluctuating, you can always buy from the grid. If you are short of power, you can use the power from the grid. If you have excess power, you can sell it to the grid. So
Power
for
purchase.
fluctuating electrical power, the solution is to buy and sell to the grid. Remember?
Yes, sir.
Uh,
So
other
is it
than
like a
exhaust.
kind of mandatory for this power plants or any kind of process industry to have a power purchase agreement with the
It
entities?
is, it is because even if you have a captive power plant, you have your own power plant in your own premises. But when you take it out for maintenance, what will you do? Your industry will stop.
Mm.
So you should have a power purchase agreement with the grid. So whenever you need, you can buy the power from them. Nowadays, with the change in rules, the import-export meters installed at your factory end allows you to sell your power to the grid also. And the power purchase agreement will mention these clauses: purchase cost, sale cost, right? Depending
Reverse
on
metering.
at what time of the day you are purchasing or selling.
Correct, sir.
Hmm. Then other than exhaust gas, what is the major source of waste heat recovery in water cooled DG set? Simple. Water cooled DG set, where they are using this water, cooling the jacket of the IC engine, isn't it? DG set. In
Correct.
DG set, the jacket cooling is done by water. Secondly, there is also another cooler for cooling your lubricating oil, right? Third
Mm.
is the cooler for cooling the inlet air or going exhaust air out of it. So these three coolers, they are recovering waste heat from the turbine, from the DG set. This hot water generated by these coolers by absorbing the heat from DG set can be recovered suitably by supplying it for any process, right? So what are the major sources of waste heat in DG set? One is jacket cooling, another is seal oil cooling, third is air cooling that is supplied to the
Sir,
DG
what
set.
is the second one? Is it Silide?
Seal oil, no
Sealed oil,
lubricating
huh?
oil.
Okay, okay.
Lubricating oil. Then L1, it's a long answer question, but it's very simple. The parameters for back pressure steam turbine cogeneration plant are given here, right? Steam turbine is back pressure, so it is exhausting into pressure and not into the condenser. Remember that. So inlet steam pressure, temperature, and total heat is given. See, you are not supposed to go through the graphs or tables and then check what is the total heat content in a 16 kg steam with a temperature of 310. No, he has already given you 9,000 kgs per hour. Outlet steam, so much kgs, so much thing. The total heat, the quantity. This is quantity. Sorry, it is not the heat. It's the quantity 9,000. The same quantity is going out because there is no steam loss in the turbine, isn't it? Find
Correct.
out the turbine isentropic efficiency. The heat, the total, this thing is quantity remains same, isn't it? So pressure and temperature here, you will have to put a formula. Isentropic efficiency will require you the two values, actual drop in uh, entropy versus the ideal drop in entropy. So heat drop for this example, is based, I think, on problems given up. So you need to have the isentropic values. Without that, you cannot calculate the efficiencies, right? So you will have to go back and see. Formulas are given, only the parameters, actually what is the quantity value, that you will have to check in the examples given above. Explain why EUF is a better indicator of cogeneration performance than heat rate. What is EUF? Energy utilization factor.
Factor.
Yeah, the formula is already there in the book. What this EUF numerator says? Numerator is the electrical power plus the useful heat used upon the fuel rate into the gross calorific value. That means total heat input and on the
E
numerator.
plus QTH by Q fact.
Yeah, that is given, no?
Yeah.
You have to only explain that formula. There is no numerical here. It's only the theory he is trying to, you have to explain.
This is more tough than problem itself.
No, but you can explain once you remember that. Then
Definitely.
this is a problem. So I will not go into each of these
Sir, I
things.
have one question.
Yeah.
So general, like for example, they're asking us to explain UF.
Hmm.
If we are not able to, like, if we feel that the answer we have written is not convincing, can we
Hmm.
just take a basic example and numerical and just show them how it works? Does that work?
But how will you take an basic example? Because you will have to assume some quantity, isn't it?
No, no, sir. Random numbers. For example, in what is this? In page 50, there's this problem, right? Energy utilization factor.
Huh.
They've just taken some numbers, uh, considering like average power output
Huh.
and what is this? 860s. Generally, like to tell this P, what are we trying to tell? Like average power output, what parameters
You,
we
you
consider?
can always explain by giving values,
Ah,
but it should not happen that your EUF is coming 150%.
no, no,
You should
definitely
know
not.
how much the range of EUF,
Hmm.
isn't it? You bring your answer to that range, and yeah, it can be explained. No problem.
Okay, done. Not necessarily like our answer somewhere, like I'm not
Ah, sure,
telling
sure,
precise
sure.
numbers.
Hmm.
Somewhere I can just remember like
Not only
70%.
that, they may ask you to calculate what is the gross heat rate, gross the fuel rate, how will you calculate the fuel rate? That kind of explanations also in theoretical questions they can ask. So
Hmm.
with
Okay.
this, I have completed this chapter. If you have to ask anything specific, I am here. Another 10 minutes we can continue. I think you are the only participant. Others have left already.
I
Hello?
guess so, sir. Manish was there. I guess he left. Yeah.
No,
There was one participant, na, sir, Manish, who had joined.
but he is not visible here.
Yeah, yeah, he left, I guess.
So that's what I say. You are the only one.
Yeah.
Okay, then. All I can do is wish you best. But
Thanks so
but
much, sir.
but lot of efforts are necessary for paper four. Huh? It's not.
Definitely, sir. I have actually looked into the question papers of
Mm.
earlier.
Yeah,
More than like knowing the concept, it's like you have to know where you have to look in that book.
correct, correct.
Though the
Uh,
answers are right in front of your eyes, you are like not able to figure out. So that is the complicated part.
But how much time you can spare for this study every day?
So frankly, for other topics, like because I'm a consultant,
Mm.
I get to read topics on HVAC systems because my somehow my profile is connected to it. So
Hmm.
those topics are going hand in hand. But I'm able to spend really less time comparatively. Like I'm getting only 1.5 hour or 2 hours to
Okay.
just go through. Probably
Yeah.
have to at least now for next 15-20 days before my
Mm.
exam, I have
Yes,
to
yes.
spend a little more time on.
Because you are attempting for energy auditor, isn't it?
हाँ sir, हाँ.
Yeah, yeah. So you will have to. Okay, then.
Exactly.
All the
I
best.
definitely need more time. I know about it, but I want to give an attempt and see how concepts are and how things work actually, to be frank.
Okay.
Yeah. but I do really want to clear at least two papers so that I have some amount of time to clear the next two papers. I think that is accepted.
Okay, okay.
Yeah.
So I think I should stop sharing it here. Here you are stop sharing. Okay, stop recording where it is. Recordings.